Good morning. Here is the science lesson for today. It is on lesson 6, acids and bases. That's what it's on. So this is, I believe, the last lesson for this chapter. Yep, I believe it is. Just verify. Oh, no, there's one more. Okay, so second to last. So if you can turn to page E82, that's where we'll begin. That's Silas. We're going to be learning about acids and bases today. Acids and bases. I'm sure you've heard about acids before. That's Charlotte. I'm sure you've heard about acids before, and you think of them as something corrosive and like eating away at things and everything like that. And so if you think of what's harmful, you might think of acids, and you think of bases as if bases are different. I have kind of some weird hair going here. If you got bases, you think of bases as different. Well, they are different, but they can still be harmful, as we're going to see. So on the first page, E82, we can see that the first thing that we find out about them is that they is how to kind of tell the difference between them. Acids taste sour. Okay, so acids have a sour taste. When you think of an acid, you might think of something like lemon juice or vinegar or orange juice, anything with a kind of a soury taste. A lot of the citrus fruits are acids, and and bases are things that you wouldn't really taste. They're things like ammonia and baking soda and things like that, and and you should never ever taste bases, but they do taste bitter. Um, you should really never taste either of them unless you know that they're safe. But but bases are like they have a bitter taste. Now, a good thing to a good way to think of them as well is by their litmus paper. What litmus paper? It talks about litmus paper in the first paragraph there. What litmus paper is these little strips of paper that you dip into a substance, and if they turn a color, um, it tells you what they are. Now, litmus paper is different than pH paper, which we're going to talk about in a second. But litmus paper, it comes in blue and red. The paper itself comes in blue or red, and you can take one of them and dip them in the liquid, and whether or not it changes color it tells you whether or not it's an acid or a base. Now, the first one, for a base, let's say, if you take base, think of base begins with B. You know what? I'm going to adjust here. I'm going to adjust like this. Okay. It just was uncomfortable the way I was sitting here. Okay. All right, that's a little better. Bases. Think of base because base begins with B. Think of, I have Nala here. As you can tell, I'm in the kids' room. Bases begins with B, and bases also, and blue also begins with B. So think of base as blue. Base having to do with the letter B, or the color blue. So if you take blue litmus paper and you dip it in a base, it doesn't do anything. It just stays blue because base always wants to go to blue. If you take red litmus paper and dip it in a base, it turns blue. Okay, so red to blue is a base. You can think of RBB. Red to blue is a base. If the red litmus paper turns blue, base. Red to blue, base. It tastes bitter. RBB. Bases are all about B's. Now, an acid is the opposite. Okay, we have red and blue litmus paper. Acids are red. Think of them as red. If you take a red litmus paper and dip it in an acid, nothing happens. It stays red. But if you take a blue litmus paper and dip it in, it turns red. So BRA, blue to red, acid. Okay, so RBB, red to blue base, BRA, blue to red, acid. So Again, think of acids as red, turning things red, and they like the color red, or if it's already red, it stays red. Bases are blue, it turns things blue, or if it's already blue, it stays blue. And acids are sour, bases are bitter. Also, when we have reactions, different things give off different particles. An acid would give off hydrogen particles. Hydrogen particle would be an H2. When we talked about a molecule, hydrogen, when it's alone without any other elements, it's seen as a doubled particle, H2. And so it gives off, those are called hydrogen particles, H2. That's an acid. When it reacts, an acid will give off H2, sometimes seen as like H2O or something like that. When a base is in a reaction, it gives off a hydroxide ion. So the H2 is called a hydrogen particle or a hydronium ion. The base gives off a hydroxide ion, which is an OH. And we talked about OHs before, things that end in OH a lot of times are alcohols. Remember I talked about that last time in the last lesson. So a base would give off an OH as part of its what it gives off. So also think about in a reaction, like remember I talked about in chemical reactions, you can tell it's a chemical reaction if it gives off a gas. That is a byproduct. If whatever comes out of it. This is a chemical reaction where the gas it gives off is either a hydronium ion or hydroxide ion. If it's a hydronium ion, it must have been an acid. If it's a hydroxide ion, it was a base. And again, a hydronium ion is an H2. Hydroxide ion is an OH. O being oxygen, H being hydrogen. Get it? Hopefully. Excuse me. All right. So there's one other type of substance. If it's not an acid and it's not a base, you put a red litmus paper in it and it stays red. You put a blue litmus paper in it and it stays blue. That would mean that it's neither acid nor base. There's only one other option. It's neutral. Just like, an electron is negative, a proton is positive. Well, if it's not positive or negative, it's got to be neutral. Well, here, the thing is neutral. And the substance that is neutral is what you think of something as neutral. It's water. Page E83, there's nothing necessarily that I want to go over on that page. It just lists out some strong acids and strong bases. You can see what happens to that statue of George Washington. It's been corroded by rain it's kind of acidic. You might hear about acid rain. Acid rain doesn't mean like rain that it falls on you and you're like, my skin is melting. It's not that acidic. It's just slightly acidic, more acidic than neutral water. And because of that, when it happens in large amounts, it can eat away at things. It happens in areas of high pollution. How can you tell if something's an acid or a base? Other than the litmus paper, which we already talked about, there's also indicators. An indicator is something that changes color in the presence of an acid or a base, kind of like the litmus paper that I talked about before. But there are some natural indicators too. For instance, red cabbage juice. Okay, if you have red cabbage juice, you see that pictured thing at the bottom of the page there, that little vegetable there. That's a cabbage. And you can tell how acidic it is by its color change. When it's that pink color, it is neutral. It gets more and more pink the more acidic it gets. However, if the substance it's in the presence of is basic, it's a base, it turns slightly basic, turns green, and very basic turns yellow. If you see it turn yellow, it's a strong, strong base. Let's see, and we talked about litmus. Litmus paper is made from a certain lichen, and the lichen has a vegetable indicator called, everybody look on the top of page E84. This is another common indicator is, I would like you to try to pronounce that word right now. Okay, I'm going to give you 5 seconds to try to pronounce that PH word. 1, 2, 3, 4, 5. Phenolphthalein. Okay, how did anybody pronounce it right? It's phenolphthalein. And so that's what happens with red cabbage juice. It has phenolphthalein in it. Let's see. All right, that's good for that page. Indicators, talk about that a little bit more on E85. All right, let's talk about the pH scale on E86. E86, a measure of how acidic something is called or how basic something is called, it will be on the pH scale. And the measure of how acidic it is called acidity, and a measure of how basic it is called its alkalinity. Okay, acidity and alkalinity. A base is called an alkaline. An alkaline is another name for a base. So we have acidity and alkalinity, and they're based on how many hydronium or hydroxide ions they have in a solution. The more hydronium ions they have, the more acidic they are. The more hydroxide ions they have, the more basic they are. And this guy named Soren Sorensen, that's kind of a funny name. If you picture that, it would be like having like a name like Patrick Patricks or Hector Hectorson. Be kind of a funny name, but he developed in 1909 a scale to measure the to kind of, you know, allow you to be able to attach a number to these different acidity or alkalinity, and he called it the pH scale. And it's lowercase p, uppercase h. It might look a little weird, but it is lowercase p and uppercase h. Now, the thing about this pH scale that's interesting, it's what's called a logarithmic scale. A logarithmic scale. Now, normal scales, normal numerical scales that we have, like, I don't know, like your weight. Your weight is a scale. Okay, when you gain 10 pounds, when you get, you know, each pound that you gain is just one more, right? Like let's say you were 81 pounds. You are 1 pound more than you were 80 pounds. And when you're 82 pounds, you're 1 pound more than 81 pounds. That sounds really obvious because that's the obvious way we make scales. A logarithmic scale is not like that. A logarithmic scale is every number is 10 times more than the number before it. Okay, so if I had something like, now, on this scale, before I go deeper into the logarithmic scale, let me tell you, from 0, it goes all the way from 0 to 14. From 0 to 7, those are acids, and from 7 to 14, those are bases. So if you're below a 7, you're an acid. If you're above a 7, you're a base. And the farther away from 7 you get, the stronger you are. So the lower numbers, like a 3 is stronger than a stronger acid than a 4. A 2 is a stronger acid than a 3. A 1 is a stronger acid than a 2. It goes the opposite way for bases. A 9 is a stronger base than an 8. A 10 is a stronger base than a 9. An 11 is a stronger base than a 10. So again, you get to be stronger and stronger. Like the strongest base is a 14. The strongest acid would be a 0. And so this is but the thing I was talking about before is a logarithmic scale. Each number is 10 times more than the other number. So an 11 is 10 times as strong as a 10. A 12 is 10 times as strong as an 11, stuff like that. And the opposite for acidity. A 4 is 10 times as strong as a 5. A 3 is 10 times as strong as a 4. Other scales that work that way are like the Richter scale, which measures earthquakes. If you have like a 7 on the Richter scale, a 7 is 10 times stronger than a 6. A 6 is 10 times stronger than a 5. Decibels work that way. You have 10 decibels, 20 decibels, 30 decibels, like that. A 30 is 10 times stronger than a 20. A 40 is 10 times stronger than a 30. Those are called logarithmic scales, and the pH scale is one of them. Let's see. Now think about this. We have